Hey guys, going to do a quick tutorial on some of the things for today. So we're going to have combinations, permutations, and some solving by factoring. So check it out. Alright, so first you've, you've got, let's talk about quickly the similarities and differences between combinations and permutations. So the similarities is that we are talking about a collection of objects. So we're talking about how many different ways can we do something. The big difference is that for combinations, the order does not matter. And for permutations, the order, in fact, does matter. So let's look at a couple of examples, see if we can distinguish which one is a permutation where the order does matter and a combination where the order does not matter. So permutation. A student or 8 students are competing in a contest. How many different ways could the judges award a gold, silver, and bronze medal? Second example. Katie has 8 friends and 3 pieces of candy. How many ways could she give the candy to her friends? Take a second, see if you can figure out which one is a combination, which one is a permutation. Alright, so the top one is a permutation. You can only give 1 gold, 1 silver, 1 bronze, and the person that gets the gold, so of the first 8 students, the person that gets the gold is certainly not going to get the silver medal. The person that gets the silver is not going to get the bronze. We'll look at this in detail, but after you pick the first of the 8, now you only have 7 people to award the silver to, and after you pick of those 7, you only have 6 more to pick for the bronze. So in this particular case, the order matters. So you may have guessed, based on that, the second case, the second question on the screen, the red one here, Katie giving candy to her friends, you have the same number of choices, three metal colors or 3 pieces of candy and 8 friends, but now it doesn't really matter who you give the candy to. So that is in fact a combination. Okay, so let's look at another example. You have how many different committees of 5 people can be chosen from? 10 people. And the second one is a special type of password consists of 4 different letters of the alphabet where each letter is used only once. How many different possible passwords are there? Take a second, see if you can figure it out. Alright, so the first one is in fact a combination. We don't care here what order the people are selected on. We're picking 5 people out of the 10. It doesn't matter who goes first in that order. We'll look at some more details in a moment. However, in the second one, it matters which ones you've already used. It says there are 4 different letters used from the alphabet, but you can only use each letter once. So in the first case, you have 26 choices. There's 26 letters in the alphabet. Second one, you only have 25 choices, and it keeps getting smaller and smaller each time you pick a new letter until you pick 4 letters. So that is a permutation because the order there, what order you pick the letters in, does in fact matter. Okay? Okay, so a familiar example is actually to talk about one of these. You might have heard them called a lock or sometimes even a combination lock. Let's see if that's actually true. Does this lock represent the number of combinations of numbers you can pick between 0 and 40, or does it represent the number of permutations that you can pick between 0 and 40? Let's check it out. So let's just make this up. Let's say that the numbers that you pick 1, 2, and 3. So this is normal. If you're actually going to put this into your lock, it has to go in that order. You have to first put in the number 1, then the next number you put into your lock is number 2, and then number 3. So it matters that you're doing it in that particular order. Also, for this example, we're going to assume that you can't use the same number twice. So for example, you can't use the combination 1, 1, 1. Just for simplicity, we'll exclude that as a possibility. So the permutations of our lock, let's assume there's 40 choices, are 40 choices on the first one. So here we chose 1, 39 choices, because we've already picked one of them. The second choice, let's say we just picked 2, and then we have 38 remaining choices because we've already picked 2. Let's just say we picked 3. So there are 58,280 permutations of that lock, different combinations or different, actually the proper word here is permutations, numbers that we could pick in a particular order that would work. But what if we did combinations? So if the lock number was 1, 2, 3, if it was a combination where the order doesn't matter, then weirdly, 1, 2, 3, according to the lock, is the same as saying 1, 3, 2, because it's the same set of numbers. Or we could do 2, 1, 3, that's the same as 1, 2, 3 if we're talking about order not mattering. So all 6 of these choices are exactly the same. So we have to divide the 6 choices out of our total. So in fact, the combination of lock would be our permutations, 40 times 39 times 38, divided by the number of ways that we could order those choices, those permutations. So we have to divide by 6, okay? So that ends up being a much smaller number. It's only 9,880 combinations that you could have of this lock. So in fact, the order does matter. So should we call this a combination lock? Probably not. We actually should call this a permutation lock, which is a super nerdy way to talk about locks, but of course that's why we're here. Okay, so this is what an example would look like in ALEKS. It says, suppose we want to choose 2 objects without replacement, so we can't use the same one again, from 4 objects, a pencil, an eraser, a desk, and a chair. How many ways could this be done if the order matters and if the order does not matter? So remember from our example before, permutation is where the order matters, combination is where the order does not matter. So we'll first deal with letter A, which is if the order matters. So here are the 12 different ways you could choose those. So for the first example, let's just say you picked 2, so you picked a pencil and eraser. The next one, let's say you picked a pencil and a desk, and so on and so on. What you'll notice is that certain of those choices, like pencil and eraser or eraser and pencil, are really the same type of thing. If it matters for whatever reason that you picked pencil then eraser or eraser then pencil, even though you have the same 2 objects, then each one of these choices counts as a separate permutation. So in fact, you'd have 12 different ways of choosing the objects. The other way to do that is on the first choice of pencil, eraser, desk, and chair, you have 4 choices. And after you've picked the first one, you have 3 remaining choices. So you just do, by counting principle, 4 times 3. Pretty simple. Now with combinations, we need to think about the order here. How many actual different iterations of these objects do we have? So we're picking 2 objects, and it would look like this. Same set of choices. We could pick pencil, eraser, eraser, pencil, pencil, desk, desk, pencil, and so on and so on. Importantly though, these 2 choices, pencil, eraser, and eraser, pencil, are the same choice. These 2 are the same, these 2 are the same, and so on. Okay? That's because the way to order 2 things, you can only order it either PE and then EP, or EP and then PE. So there's only 2 ways to order each of those choices. So what you do is you take 12 over the number of ways you can order it, which happens in this case to be 2, and so 12 divided by 2 is 6. Let's do another quick combination question. So a small acting club has 6 members. 3 of those members are chosen for a trip to see a Broadway play. How many different 3-member groups are possible? So there's 6 choices, and we're picking 3 of them, or 6 members. We're doing combination. So here, the order does not matter. What we mean by that is if we sent, Tim, Sally, and Joe, it doesn't matter what order we send them in. They're all the same group of 3 people. Okay, so this was sort of the formalized way to represent what we've been talking about. You take the number of permutations divided by the the number of ways you could order those things, and they're using fancy symbols here, not a big deal. So there's 6 people, and we're picking 3 of them. So you do 6 times 5 times 4 over how many ways you can order 3 different things. If you'd like, take 3 scraps of paper, label them A, B, and C. See how many ways you can order them. It turns out when you do that, you do 6 times 5 times 4 because you pick 6 people, then you have 5 people to pick from, you have 4 people to pick from, and it turns out you can order 3 things 6 different ways. The first choice you have 3, then 2, then 1. So you do 120, that's the numerator divided by 6, which is the denominator, and you get 20. There are 20 different groups of people that you could send. Again, here it doesn't matter which person in the group comes first. Let's try another quick permutation. This is sort of a visual way to see what we've been talking about. 8 students are competing in a contest. How many different ways could the judges award a gold, silver, and bronze medal? So, of course, if the first student gets a gold medal, there are only 7 people left to get the silver, and after that there's only 6 to get the bronze. So you have 8 choices. The first one gets gold, the second gets silver, the third gets bronze. So you end up with 8 times 7 times 6. That's 336 different ways that you could award those medals. Now, if it doesn't matter what order we're going in, so we're going to do a combination. So Velma has 8 friends. She's giving out the candy. This is the example from earlier. How many different ways she could give out the candy to her friends so that each person ends up with a piece of candy. So the way it ends up working, let's say she has 8 friends to choose from, and this is the cast from Scooby-Doo. Let's say she picks of her 8 friends, Fred goes first, and then now she only has friends 2 through 8 to pick from, so 7 total friends to pick from. And then let's say she picks Boo Boo. Now there's only 6 friends to choose from, so if she had 8 choices, then 7 and 6 choices. So the number of ways, if it mattered that Fred went first, then Boo Boo, then let's just say Barney went next, there'd be 336 choices. But we're not done yet because we want to know combinations. It doesn't matter if Fred goes first or if Boo Boo goes first. So remember, you could go Fred, then Boo Boo, then Barney, or Fred, then Barney, then Boo Boo, or any of these 6. These are the 6 different ways you could order those 3 people that are getting the candy from Velma. And so what we need to do is divide both sides by 6. Those 6 permutations are all identical if we don't care what order we hand out the candy. So we need to divide by 6. That's on the top we have the number of permutations. On the bottom we have how many different ways you can order them. So when you end up dividing, you have 56 different combinations of friends. Oops, friends, not dogs, different problem, sorry. We have 56 different ways that you can order or give candy out to 3 friends out of 8. Okay, so with the little bit of time we've got left, I want to just quickly remind you how we do factoring by grouping. So what we do is, of course, in a situation like this, we're going to group the 2 terms that we've factored out of our grouping. So we have 4x minus 9, that'll become the first term in our grouping. The second term will be x plus 4 because that's the same in both of them. Then you just smush them together, and this is our factored problem. Now, the thing you're going to be talking about now is solving by factoring, and you're possibly going to be introduced to a new shape on a graph. It's called a parabola, and that comes when you multiply 2 things that have an x in it together. What we're going to try to do is solve and find out when the parabola equals 0. So let me show you what that looks like. So just start with an example, and we'll look at the one from our notes there. But if we start with x plus 2 times x minus 2, we get this shape on our graph. And it turns out there are 2 places where a green graph here crosses the x-axis. The one we just talked about, which is this parabola, looks crazy. It looks like this. What we're going to know is where the parabola crosses the x-axis. So it apparently crosses at -4 and at 2.25. We're going to figure out where that comes from. So where that comes from is we take our 2 factors and we set them equal to 0, where the graph crosses the x-axis, and then we just simply solve for 0. So by adding 9 to both sides, we get 4x equals 9, and then dividing by 4, we get x equals 9 over 4. The same deal over here. We get x plus 4 equals 0, subtract 4 on both sides, so that we get that our solutions, or where the parabola across the x-axis, are at 9 over 4 and x equals -4. Just to verify, indeed, our parabola does cross at -4 and 2.25. Let's double check. That's 9/4. Yep, 9 over 4 is 2.25. Really quickly, let's factor this. Okay, so if you do the appropriate factoring, you end up with these 2 terms. Let's see what that looks like. All right, this crosses the x-axis at -1 and 0.6. 0.6 is the same as 3/5. Let's double check that that works out. So on this one, if we take 5x minus 3 and set it equal to 0, solving it, we get x equals 3 over 5. On this side, we get x plus 1 equals 0. Solving that, we get x equals -1, confirmed by our graph. Nice work.